Section 3.8 is titled Kinetic Energy of Rotation, comma, moment of inertia. And what this section is about, when we're talking about electrical machines, these machines outside of transformers are rotating devices. So we got this concept of kinetic energy, kinetic meaning energy of motion, in the section prior. But what we need to do is we need to understand about kinetic energy in relationship to something that is rotating. So we need to quantify that and to be able to work with those types of situations. To do that, we look at this equation 3.8, which gives us an equation for kinetic energy of rotation. Let me point out a few things to you. First off, again, this is given as energy sub K. It's going to be in joules. This constant is 5.48 times 10 to the negative 3. This is a constant, and he mentions in the description of the equation that it is a constant to take care of units. Now, what that means is we're trying to work through problems, and we're basically signed up for SI units, but sometimes there are some parts of an equation that might not use SI units, and so what this does, it gives us this constant that adjusts our equation so that we can work through it, I guess basically is the easiest thing to say about it. We don't want to spend all our time, worrying about derivations of things like this. We take that as engineers, technologists, technicians, and we get that constant and we use it in this problem or in an equation like this. Now, something that is unique to this section, and it's brand new for us here, this is called the J number. And the J number is described as the moment of inertia. And for the time being, just know that it is measured in kilogram meters squared. Don't confuse this J number with joules, because that's not what it means. It is a description of the actual thing that is rotating. And I'll show you we'll go into a lot of detail about that in just a second. And then the other thing I want to point out to you is, here we go. Our speed is squared. This is n squared, and it is in RPMs. Okay, remember our equation for linear motion was in meters per second. So we're kind of going back and forth between some things, but we've got equations, and all of this stuff is equation based, and that's what we want to work on. When doing problems that are involving kinetic energy of rotation, a revolving energy possesses kinetic energy. Its magnitude, given by that equation 3.8, depends upon the speed of the rotation and the mass and shape of the body. Okay, the mass and shape of the body is described by this thing we're going to call the J number. And as you look at this figure 3.5, and we'll walk through these, looking at some of these and discussing what this J number means. But what he does here, he gives us this thing called a moment of inertia, which is described by a letter J, and J depends upon the shape of the rotating thing, device, object. Okay, and so in figure 3.5, we have a shape that is this, which looks like a square, rotating about a point of axis with a radius r. It's rotating, has a certain mass, And we can describe that moment of inertia as m equals r squared. And that is descriptive of this situation. Okay, all these are listed on page 55. Let's go to another one. Let's say we had a solid disk of mass m with a certain radius. Okay, so this is a solid disk that's rotating, and we have a J number associated with this that is unique to this particular shape, and that is the mass times the radius squared divided by 2. We don't have to worry about the derivation. We're given this number, and we just want to use it. Another one that we run into often is what's called an annular ring. Okay, it's not solid, in other words, and it has a certain mass and a rectangular cross section. So it actually, you know, we're looking at two radiuses, one from the point at the center to the outside, one at the point of the center to the inside of this annular ring, and it's rotating, has a certain mass, and it has its own J number, and its J number looks like this. Now, even if we were meeting in person and all, of course, I would not expect you to memorize these J numbers. Let's fill our brain with other things, you know. All we want to know is where to find that J number. We need to know where it is so that we can access it. Another J number is given to us in figure 3.8. It is a straight bar that has a particular length, and the straight bar has a particular mass. And if we want to know its J number, our moment of inertia, again, that concept may be a little, not exactly clear, but just know that there's this concept, this moment of inertia that's attached to every rotating object. And that number is unique to the shape of the object. And if I have a situation such as this, that J number is equal to this. All right, each one of these are given equation numbers. I haven't been numbering, but this is 312. We started with 39. And then the last one that we'll look at, and then I'll stop this video and we'll make this two parts. The last one is, here's this rotating object, and it is, here's the center, and it's rotating, you know, about that center. And again, we have two radiuses. One is the center to the end of the device or object. The other is the center to the beginning of the object. And those two radiuses are shown in the J number for this, which is pretty complex. If we look at this M mass divided by 3, and it's equal to R1 squared plus R2 squared plus R1 times R2. That almost looks like something out from a parallel circuit resistance calculation. But anyway, we have access to these J numbers, and we're going to use those when we do calculations involving kinetic energy of rotation. Let's stop there and make this, we'll make this part 1 of this section, and then I'll do another one here, and we'll work a problem.